In earlier videos about the theory of incomplete measurements, we saw that physics is all about measurements, and that, as a consequence of all measurements being discrete, there is no continuum, no space and no time, only discrete measurements of space and time. We also observed that variables and equations are not the correct model to deal with discrete measurements. In this video, we are going to discuss about a statistical approach that works much better, and how the continuum can re-emerge from that approach. Let us start with heads or tails, a very simple form of measurement giving only two results. Looking at a coin, you recognize either head or tail. We also know how to flip a coin to get a random result. So we have a tabletop experiment with a process creating some random state, and then a measurement of that random outcome. We all know that there are 50% chances of getting head and 50% chances of getting tail. When we say 50%, this literally means 50 out of 100. It's a statistical probability. In other words, while each throw is random, we still know something about a large collection of throws. Our knowledge of this experiment is statistical. The precision of this knowledge increases with the number of throws. If we throw 100 coins each time, we will still see some variations in the observed percentage. However, if we start accumulating the results of thousands of throws, we will soon see the observed probability converge towards 50%. This is not a quantum mechanics experiment. But like quantum mechanics, this is an experiment where a given individual result is random, and where the law describing the experiment only tells us the probability of getting each possible outcome, not the actual measurement result. We can repeat the experiment, and count how many times we got each possible outcome. This gives us a vector with two natural numbers, one for heads, one for tails. The theory of incomplete measurements calls probavectors such a vector, counting each possible outcome of an experiment. It calls certivectors the outcome of a single measurement, which means a probavector where the sum of all components is 1. In the case of heads or tails, there are two certivectors. We can conventionally name them heads and tails, after the result of the measurement. Probavectors will take the general form of n heads and m tails, where n plus m is the total number of experiments. In other words, the probavector describing an experiment is the sum of the certivectors for each individual measurement. For example, after 100 draws, we might have 55 heads and 45 tails. Mathematically speaking, certivectors are a basis for probavectors. As we repeat throwing coins, the probavector moves, representing the accumulated knowledge we gained out of individual measurements. We can draw this accumulation by plotting the successive positions of the probavector as we draw 100 coins. As you can see, the trajectory varies from one series to the next. This is unsurprising since we are talking about random events. We can interpret this buildup of information as the exact opposite of what is called the collapse of the wave function for the system in quantum mechanics. In other words, instead of the wave function collapsing for one measurement, here we make it emerge experimentally out of individual measurements. To illustrate the veracity of this statement, let us consider Thomas Young's well-known interference experiment. More specifically, the variant where photons are sent one by one. Quantum mechanics predicts that the outcome of that experiment matches the wave function of the photons. The theory of incomplete measurements considers each single photon impact as a position certivector, and their accumulation as a probavector. Consequently, the probabilities from the resulting probavector match the amplitude of the quantum mechanics wave function. Like a wave function, a probavector can therefore also represent a prediction. In that sense, probavectors unify the theoretical and the experimental representations of knowledge. For example, a probavector predicting heads and tails would be something like 50 heads and 50 tails. One should be very careful, however, as shown with the experiment you see on the screen. Here, we draw heads and tails 100 times in a row, and then plot the resulting probavector on a grid. As you can see, the actual result of each experiment is, generally speaking, in the right direction. However, it is not precisely aligned with the diagonal. When we draw at random, we don't get exactly the same number of heads and tails. Incidentally, the picture that emerges over time on this two-dimensional grid is a probavector for the probavectors. This suggests that in the theory of incomplete measurements, laws of physics are themselves represented by probavectors. We will explore that further in the next video. For now, let us simply consider a derived measurement, which consists in counting how many heads we had after 100 throws. This derived measurement has 101 possible numerical results, from 0 to 100. We can visualize the probavector for the derived count using something called a histogram. This allows us to visualize probavectors with a large number of components. Notice how the histogram that emerges from a large number of experiments is no longer random. Rather, it takes a shape known as a bell curve. This bell curve is predicted by what is known as the normal law. The demonstration of the emergence of such a law is called the central limit theorem. This effect explains how an accumulation of random events can lead to non-random, deterministic distributions of probabilities. This is how the theory of incomplete measurements explains what is sometimes called quantum decoherence, that is the emergence of deterministic laws of physics from the accumulation of random experiments. The more possible outcome there are, the more the curve looks like a spike. When you deal with 1 liter of water, you are talking about a number of water molecules that is written with 26 digits. This means that even if individual molecules may have a somewhat random speed and position, their average speed and position is quite deterministic. Together with determinism, the continuum also emerges from the accumulation of a very large number of discrete events. From the bell curve, for example, we can compute an average value for the number of heads or tails. While the count of actual measurement results is a natural number, the average value itself is not. It is a rational number, the ratio between two natural numbers. Furthermore, the limit as numbers grow larger and larger may be irrational. If we count how many pixels there are on a circle on a computer screen, and divide that by the number of pixels across its diameter, the ratio mathematically converges towards pi as the circle grows larger. That remains true even if no individual measurement of that ratio will ever give pi, since pi is irrational. When the difference becomes small enough, reasoning on the continuum may prove much simpler. We have this experience from daily life, where we talk about kilograms of sand or liters of water, and totally ignore how many grains of sand or molecules of water that actually represents. When the precise number of molecules requires 26 digits, it is much simpler to treat it as a continuous mass of molecules. In the theory of incomplete measurements, such measurements are called massive. This means that we treat a very large mass of individual events collectively, and replace it with a continuous variable that is much simpler to deal with, both mathematically and practically. Whenever the massive approximation is valid, so are the classical mathematical tools used in physics for centuries. In other words, a discrete histogram with trillions of distinct measurements can legitimately be replaced with a function of a continuous variable. As long as one remembers that this is an approximation, and the conditions for its validity, it is perfectly safe to do so. This is the new meaning we shall give in the rest of these videos to variables like force, mass and acceleration in classical physics. We said in an earlier video that Newton's second law remains true in the theory of incomplete measurements. This is the precise meaning of that statement. In this video, we have seen how we can represent the knowledge about measurements using probavectors, how deterministic laws can emerge from random events, and how the massive approximation gives us back the familiar continuum and real numbers. We also observed how probavectors can be used to represent laws of physics. In the next video, we will focus more specifically on this question, to discover the relation between equations and probavectors.